Hi everyone, welcome to Gateway Lectures. Today we are having here solutions for quiz day 16 and here we have a question number 1 and today's topic is all about unconventional machining and also CNC and powder metallurgy of the production. By today the production syllabus will be finished. Tomorrow we'll be doing with industrial engineering and then after that the final day we'll be doing mathematics, and again the cycle repeats from the starting as we done from the starting with thermodynamics. Again the cycle repeats. So today let's start with the first question. The composition, that is percentage by weight, of mnemonic alloy, the mnemonic 75 alloy is given. Okay, and the composition was given as nickel is used 72.5% by weight, chromium is used 19.5%, ferrous iron was used 5, titanium was used 0.4, and silicon was used 1%, manganese was used 1%, and copper for 0.6%. Calculate the removal rate, nothing but a metal removal rate, in centimeter cube per minute when a current of 1000 amperes is passed. Use the lowest valency of dissolution for each element. Okay, and the atomic weight, valency of dissolution, and the density of the important elements were given in a table. So here they gave a table for us. From this table we need to select take the required data, whatever is required for us. And first we will see what is mnemonic alloy. Mnemonic alloy are called as the super alloys because they are nickel based alloys, and these alloys have a special property that even at high temperatures they can sustain the creep, so they will have very low creep. So these type of alloys are called as super alloys, and generally these will be used in turbine blades, gas turbines where there is a high temperature working. So creep is a main problem in the gas turbines. So in those places we will be using these type of mnemonic alloys which are nickel based alloys, right? And so you need to calculate all this. First of all we'll see the mechanisms of this is a question on electrochemical machining, right? Because here it is said to take a valency, and it is in the question itself it is mentioned dissolution. The dissolution is a mechanism, ionic dissolution is a mechanism in the electrochemical machining. So we'll see electrochemical machining first. Here we'll see how to extract formula. We'll see the working of electrochemical machining. We'll extract the formulas from the working, and then we'll use that formula here to calculate the final metal removal rate. This is the working of an electrochemical machining. Here we will be having two parts. One is the anode and other is the cathode. Always remember, in unconventional machining, whenever you are seeing electrochemical machining or electric discharge machining, in this type of machinings, every time our tool will be the cathode. Okay, cathode generally will be connected to the negative terminal of an electric power supply, and generally anode will be connected to the positive terminal. Okay, so always our workpiece will be the anode and our tool will be the cathode. Always you need to remember this. Then this is called the electrolyte. Whatever is you pump into this workpiece through the tool into the distance between the workpiece and the tool. Generally this is our tool, okay, and this is our workpiece. We'll make with some other color. This is our workpiece. In between the tool and workpiece, before the current is passed, there will be a substance called electrolyte. Okay, and this electrolyte is generally a conducting material. This electrolyte is generally a conducting material which helps in transfer of ions. Okay, positive and negative ions, by which ionic dissolution happens. Now we will not go into the deep how the electrons will how the ions are transferred, how the dissolution happen, but we will see the basic outline of this electrochemical machining working. This is an important unconventional machining in complete unconventional machining chapter. This is an important thing. This will be having the highest material removal rate. Okay, amount of material removal rate will be higher here, and the material removal is on the workpiece, that is anode, and material is removed by the cathode. Okay, and things to note here is generally this for this the power source, whatever we use, the power source should have high current and low voltage. Okay, why we need high current? Just now we'll see that high current and low voltage, and that too will be giving our power through DC supply, direct current supply, not alternating current. We are giving it to direct current supply. Okay, and what is the governing law for this ECM is Faraday's law. Faraday's law is the governing law, and according to Faraday's law it is said that amount of metal removed is directly proportional to the amount of the charge flown per unit time. Amount of charge per unit time, flown per unit time. Nothing but the amount of charge flowed through the conducting material per unit time is directly proportional to the amount of the material removed on the workpiece, right? So, and from this we can see, we know the amount of metal removed is nothing but mass, and the amount of charge flowed per unit time nothing but Q, and that per unit time is generally it is a charge which is being flown per unit time, and this can be written as, we know, Q is equal to I into T, right? So the mass is directly proportional to I into T, and removing the proportionality, it will be M is equal to Z into IT. Fine. Z into IT, and this Z is called as the Z is a proportionality constant, and here it is called as electrochemical equivalent. Since we are using the process of electrochemical machining, it is called as electrochemical equivalent. Okay, we'll see the remaining derivation from here. From M is equal to Z80. Here our whatever conducting material is coming here, it carries out, it takes along with that the diluted metal particles of this workpiece, and again it will be sending into the chamber which holds all that electrolyte. Again it is filtered and pumped back into the filter. Through the pump, again it is filtered through the tool. This is a basic functioning. Here we will be supplying electric power, negative electrode to the tool and positive electrode to the workpiece. We will see the remaining calculations from here. See, M is equal to Z into IT, just now we obtained, and this Z is called as electrochemical equivalent, and that Z can be given by E upon F, and this F is called as the Faraday's constant. Since the Faraday gave the law, it is called as Faraday's constant, and its value is equal to 96500 coulomb per mole. Generally coulomb is the unit of charge, right? So it is coulomb per mole. So mole is nothing but the amount of substance, and here E is called the gram equivalent, and generally this gram equivalent is given as, the name it is gram, nothing but atomic weight upon valency of the given material, given workpiece material, right? And atomic weight, we know generally it will be in gram per mole, and valency have no unit. So to cancel out this mole, this Faraday's constant also have the mole term in the denominator. So that is all about Z, and the E can be calculated by atomic weight upon valency. Once M is equal to Z is nothing but E upon F into IT. Okay, from this we can write M by T, nothing but the mass flow rate, is equal to M by T is equal to EI upon F. Okay, this is called the mass flow rate, and to get the volume flow rate, we know we should divide it by density. So for volume flow rate, it is EI upon rho F. Okay, and this EI upon rho F is nothing but the MRR, and in our question we need only till up to this, and there are few other terms, specific MRR and also feed rate. These are not required for us. These are till here, this derivation we need. Okay, so we will be using this equation finally. MRR is equal to EI upon rho I. So we will write that MRR is equal to EI upon F rho. So MRR is equal to EI upon F rho. In the question I was known, it was given, and F is a constant, it is also known. I was given 1000 ampere. We need to calculate the value of E, gram equivalent, and the value of the density. But here it is given an alloy. How to calculate the density of an alloy when the mass percentages were given, when the weight percentage was given is. So the density can be calculated in this way. Density rho is equal to of the alloy. So let this be named density of alloy, mnemonic alloy, is equal to, generally the mass percentage is given for 100. So 100 upon, now we need to take the question here. 72.5% we are using nickel, and what is the density of nickel here? From the table you can observe, here is our nickel and the density is given as 8.90. Similarly for chromium, it is having 19.5%, and for chromium is here, the density is 7.19, and for ferrous it is said that 5% it is used by weight. Then here in our table we are having ferrous here, and it is having the density of 7.86. Similarly we will mark all the elements required. We will mark all the elements required given in the question. We will be using them. Okay, how will you use them is 100 upon the density of nickel 72.5 upon the percentage of nickel by weight 72.5 upon the density of it 8.9. Similarly, the next thing is chromium. So similarly, chromium percent was given 19.5 upon its density 7.19. And then ferrous was said that it is 5%, so 5 upon density of ferrous is 5.86. And after ferrous we are using titanium. So for titanium it is given percentage as 0.4 and the density is 4.51 from the table. And after titanium we are using silicon, it is said that 1% and the density is 2.333. And after that we are using manganese, and manganese also at 1%. Upon manganese density is 7.43. And finally it is copper. Copper is 0.6%. So 0.6 upon the copper density is 8.96. So in this way we will be calculating the density of an alloy. So generally in gate examinations or in engineering service examinations, mostly a single metal will be given. Then solving that question will be very easy. Even just you learn some concept, solving this question will be easy. But you need to solve these type of tricky questions. In these questions, alloy is given. So first of all, you need to calculate the properties of an alloy. So here the density of alloy is calculated in this way, and once the density was known, the density of alloy will be coming out to be under calculation. It will be 8.18 gram per cc. Nothing but 8.18 gram per centimeter cube. And here rho is also known. Now we need to calculate the gram equivalent E. Generally for single substance, gram equivalent is equal to atomic weight of that metal upon the valence of the metal ion. But here it is given an alloy. So how will you calculate for alloy the gram equivalent? You need to understand. It is calculated as 1 by E is equal to. These all relations can be obtained mathematically. It is very easy to obtain them. But here directly I am taking the relation how to calculate. And it is said in the question 72.5% of nickel is used, and in the question it is said to consider the lowest valency of the dissolution for each element. See, if you can consider the valency chart here, you can see 2/316, 2/3, 1/2, 2/3. So there are two valencies given. As mostly metals will have the two valencies. One will be close to the lower orbit and the other will be to the outer orbit, to the next higher orbit. They can have two valencies. Either plus or minus, they can have two valencies. So we need to consider two valencies. So if we consider for chromium, the least valency is 2, and then for copper the least valency is 1, and for the ferrous the least valency is 2, and for nickel the least valency is 2, and for titanium it is 3, and for silicon it is 4, and for manganese it is 2. So we'll use all these valencies in the question, in the solution. So 72.5% of nickel by 100 into the valency of the nickel is, the least valence of the nickel given in the question is 2, and upon its atomic weight. Now we need to consider their atomic weights, respective atomic weights. They were given in the first column, right? You can consider them, and I am directly writing the values here. Upon 58.71 plus 0.195, nothing but 19.5% of chromium, into the valence of chromium, least valence of chromium is 2 upon its atomic weight 51.99. Similarly 0.05 into 2 upon 55.85, that is for ferrous, right? And then after ferrous it is titanium, and for titanium it is 0.004 into 3 upon 47.9. And after titanium we are having silicon. So for silicon 0.01 into, nothing but 1% is given, right? So 0.01 into valence of silicon is 4 upon 28.009 is its atomic weight. Similarly, and the last two elements are manganese and copper. So for manganese it is given 1%, so 0.01 into valency upon 54.94 is its atomic weight. And then finally comes our copper. And for copper again it is said 0.6%, nothing but 0.06 into its valency is 1 upon 63.57. Once we substitute all this, then we'll be getting our value of E, and the E comes out to be 27.68. Okay, the value of E is also obtained, nothing but a gram per mole, right? Now E was known, rho was known, F was known, I was known. We'll substitute here and we'll be getting the MRR. E was 27.68 into the current given in the question is 1000 amps upon the Faraday's constant we know 96500 coulomb per mole into the density we calculated here 8.18. then our answer comes out to be MRR is equal to 2.1 centimeter cube per minute, because in question it was asked 2.1 centimeter in centimeter cube per minute, and this will be our answer for this question. We've just taken time to discuss how ECM functions, and we derived the formula and then we applied that. So this question took some time. So we are entering the next question. In this question we will not make any derivation, because electric discharge drilling generally you can notice from so you can read from some standard textbook. Here directly we will solve the question here itself. Generally in electric discharge machining it is by a spark erosion technique. So the mechanism is spark erosion. So it should produce some spark. How can we produce spark? By using some electrical circuit. Okay, spark is produced due to high voltage gap. So we should produce a high voltage, that is nothing but a discharge voltage, right? So between the spark we will be having some voltage, it is called as discharge voltage, and for supply also we will be giving some voltage, it is a supply voltage, nothing but the V0 that we will discuss in the question. And there will be a RC circuit. We will just discuss the circuit here first. Okay, before that we will go through the question. During an electric discharge drilling, so we are making drilling operation of a 10 mm square hole in a low carbon steel of 5 mm thickness. Okay, brass tool and kerosene are used. Generally brass tool was used and kerosene is used as an dielectric fluid. Okay, there is a function for dielectric fluid. Here we can't discuss that, again we will discuss it later in the concept series. The resistance and capacitance in the relaxation circuit are 50 ohms and 10 microfarads respectively. The supply voltage is 200 volts and the gap is maintained at such a value that the discharge sparking takes place at 150 volts. Nothing but the discharge voltage was given 150 volts. The time in minutes required for the complete drilling operation. So what will be the time required in the complete drilling operation? So the time it will include both charging and discharging time, right? And also the frequency of the sparking is given. The frequency of sparking, V is equal to 1 upon Tc. V is equal to 1 upon Tc. Nothing but when it will discharge, whenever the circuit gets charged to the complete threshold level, then it need to discharge the charge. So it will discharge. So for each discharge time, there will be a gap between each discharge. So that is called, then we can calculate the frequency. And here the Tc was given, the equation was given. Tc is equal to 1 upon Tc is equal to 1 by Rc, natural logarithm of V0 upon V0 minus Vd. And also here the Vd is called as the tool gap voltage, nothing but the discharge voltage, and V0 is called the supply voltage, and R is the resistance, and C is the capacitance. And here energy, generally we know it is when a capacitance and voltage circuit was used, the energy delivered is half CV square. So here, since it is delivered in the form of discharge during spark production, so it is half CVD square. And MRR, here a relation for MRR was given in terms of average power input, right? And then MRR is given as 27.4 at capital W whole power 1.54, and the capital W is said to be average power input, and where Q in mm cube per minute and W in kilowatts. Okay, first we'll see the circuit and then we'll just proceed into the question. So this is a RC circuit used for electric discharge machining. Generally this tool and workpiece will be in a medium of dielectric fluid. Generally it will be kerosene, and here the tool is cathode and workpiece will be the anode, the same. And here this is the RC circuit, this is the resistance used, and capacitor is connected in parallel to the circuit, and it is a capacitance C, and V0 is the supply voltage, Vd is the discharge voltage, nothing but the voltage across the terminals between the tool and workpiece. So in our question it is given 1 by Tc. Here we will not making any derivations here, because this question we can directly solve from the, just to know, we know the mechanism and we can directly solve from the given conditions only. 1 by Tc is equal to 1 by Rc ln V0 upon V0 minus Vd. Okay, and in the question Vd was given as 150 volts and the supply voltage was given as 200 volts, right? And so from this the Tc, nothing but the time period between the sparking, when it will spark, whenever it will spark is after charging, just after charging it will spark. So 1 upon Tc is equal to Rc ln V0 upon V0 minus Vd, right? And here, from here R was given in the question as 50 ohms and C was given 10 microfarads, so 10 into 10 power minus 6 into natural logarithm of V0 200 upon 200 minus of 150. And from here here comes our time. Okay, that is our time required to discharge the spark. Okay, this is the time period for spark, and this time whatever we are getting is the time required to discharge the spark, and the time is 6.93 into 10 power minus 4 seconds. So our spark will be discharged in this amount of time. It is not the charging time, it is a discharge time. Okay, in the discharge it will be happening in the form of spark. This is the discharge time. After getting discharge time, we need to calculate energy here. Energy is given in the question, half CVD square. Half CVD square, and half into the capacitance is again 10 into 10 power minus 6 into the value of VD was given in the question as 150. So 150 is whole square. Okay, and average power is nothing but this is the power that is discharged. This is the amount of power energy that is used while discharging. That is why we are taking discharge voltage. Okay, so the half is equal to energy stored in the capacitor. To be exactly, it is energy stored in the capacitor, half into CVD square, and that energy we will be getting from here. E is equal to half CVD square, and generally the W which was given in the question is average power input, and that is nothing but the energy upon the time of discharge. Energy of discharge upon the time of discharge. We have calculated the both. So half into 10 into 10 power minus 6 into 150 square upon the time for discharge is just now calculated 6.93 into 10 power minus 4 seconds. Okay, from here it comes the average power 0.6233 kilowatts, and this is the average power delivered during the discharge. This is the average power used for machining. Okay, and in the question we are asked to calculate the volume flow rate, volume of metal to be removed. Not exactly, in the question we are asked to calculate time in minutes, total time in minutes. So for that what we will do is, in our question there was a relation given between MRR and the average power. MRRQ is equal to 27.4 W power 1.54. So MRR is nothing but volume upon the time, but here the time is a total time. Why the total time? Because whenever we are taking the material removal rate, then it is a total time that is considered between the charging and discharge time, right? Whenever we are saying we are doing a machining operation in this type of idiom, then the circuit has to charge and then again it has to discharge, again charge and again discharge. So it is a total time in which we are calculating the MRR. So MRR is calculated per that time. So in that time, what is the volume removed is nothing but the MRR. So we'll know what is the volume removed. For the volume removed, it was said in the question 10 mm square hole has to be made in the steel of thickness 5 mm. Then the volume will be 10 mm square hole. So into 10 mm into the thickness is 5. So that comes out to be 500 mm cube is the volume to be removed. Right. And so volume was known. Q is equal to 27.4. The W just now we have calculated 0.16233 whole power 1.54. Now the volume is also known 500. So what we'll do is directly we'll take the T total from this equation. T total is equal to the volume upon 27.4 into 0.16233 whole power 1.54, and the volume just now we've done, it is 500 upon 27.4 into 0.16233 whole power 1.54. From that the total time we'll be getting, that means the total time required for the material removal, not but the total time required to remove the desired material from the workpiece. Okay, and the time comes out to be, they were asked to calculate in minutes. Okay, it comes out to be in 300 minutes. So it will take 300 minutes to do this operation. It is very slow, but these type of operations will be used for mostly for hard materials or materials which gain some stress during machining. Okay, for that material we will be using. And also in the question, the Q is given in mm cube per minute. So whatever Q we are taking here, it is mm cube per minute. Then the time whatever we are getting will be in minutes. Okay, and that comes out to be 300 minutes. And here comes our next question. Question number 3. For cutting a 120 micron wide slot, and this is the electron beam machining. We will also see how the electron beam machining functions and also few empirical relations in electron beam machining here. First we will go through the question. For cutting a 120 micron wide slot in a 1.2 mm thick tungsten sheet, electron beam with 5 kilowatt power is used. Okay, determine the speed of cutting. First we need to find the speed of cutting, at what speed the cutting is being done. And also if the specific power consumption in EBM, generally wherever we see specific power consumption, it is nothing but in terms of machining, it will be the power upon MRR. So here also the same units were given, 12 watt upon mm cube per minute. That minute was brought into the numerator. Also determine the electron range. We'll see what is electron range. If the accelerating voltage is 150 kilowatts is used for drilling a hole in the steel workpiece, right? So these were the two questions. In one question we are using tungsten sheet. For that we need to calculate the speed of cutting. In the second question we are using a steel workpiece for which it is having a density, and for that we are using a 150 kilovolt accelerating voltage. Then we need to calculate the electron range there. So what will be the electron range in that case? So we will be getting two answers here. So we will see the functioning first. So this is the functioning of electron beam machining. Here high voltage current will be given from the transformers, 30 kilovolt, and the DC power will be given here. Once the 30 kilowatt DC power was given to the electron producer, it will be a particle accelerator or a particle producer. There will be a cathode bridge from which there are two anodes. Generally electron anode is nothing but the anode is nothing but it will be connected to positive charge, right? Why we are kept two anodes? Because just to suppose if we keep one anode, these electrons what we are having, those will be attracted towards one side. So to avoid that we placed the balancing anodes on the both sides, and then it will be passed into a lens. Okay, it was passed through a lens to be focused on a certain area of the workpiece. Okay, through in the vacuum chamber, these electrons will be passed onto a workpiece, and these electrons which are having high kinetic energy, whenever they go and strike the workpiece, that kinetic energy is converted into thermal energy. Nothing but the electrons which are highly penetrating. Suppose this is our workpiece. The high kinetic energy will come and strike. The kinetic energy of the electrons, high kinetic energy, will be coming and striking here. And after striking, since due to the lattice, since the workpiece is nothing but the metal, and it will have some lattice structure, and in lattice structure there will be atoms. So due to the lattice distortions and the lattice resistance, they will only travel to some distance, and when traveling through this distance, that kinetic energy is completely being conserved, and that is conserved in the form of heat. So heat is being generated here, and that heat, whatever is generating, just melts away the metal, and this metal is nothing but the metal is removed from the workpiece, melts away, and also it vaporizes. Here melting and vaporization both happens at a time due to this high velocity electron being traveled. Okay, we'll also calculate the velocity of electrons here. We'll see in the empirical relation, just generally we'll be using here. One of the empirical relation will be the velocity of the electrons, and the velocity of the electrons, there is an empirical relation given as 600 into under root of V. V is nothing but the accelerating voltage. Okay, that is given in the question. And the second thing is we'll be using electron range. What is electron range? See here I've said due to lattice resistance, it will penetrate only to some thickness, to some distance, right? And this distance is called as the electron range. So the distance through which the electron penetrates into the workpiece is called the electron range. And even for that, this workpiece will be having some density. So for that, an empirical relation was given, and that empirical relation range generally denoted by delta. It is said that 2.6 into 10 power minus 17 into V square, nothing but accelerating voltage upon the density of the metal. Okay, so these two equations we'll be using here to solve this question. So let's proceed to the solution. So first of all, we'll be taking two parts here. Let this be first part. That was the first part asked in the question. This is for tungsten sheet, right? And other is for tungsten sheet, and other is for steel. It was given in the question. So for the tungsten sheet, the data was given specific power consumption. We know the specific power consumption is nothing but power upon. So specific power consumption is nothing but the power upon MRR. Okay, and here in our question, the specific power consumption was given as 12 watt minute per meter mm cube, and also the power used for electron beam is also given 5 kilowatts. So the power is known and specific power consumption was known. From that we can write the MRR. MRR is equal to power upon specific power consumption, right? And the MRR we can write generally. MRR will be volume flow rate. That volume flow rate generally we can write it as area into velocity. So we'll be writing the same, area into velocity. That is equal to the power given in the question 5 kilowatt, nothing but 5000 watts, upon the MRR given in the question 12. Okay, and the area, here area is nothing but, it is said that 120 micron wide slot should be made in a 1.2 mm thick. So it is 120 micron, nothing but 120 into 10 power minus 3 mm into the thickness of the sheet is 1.2 mm into, we need to calculate the velocity, is equal to 5000 upon 12. Okay, from this we will be getting the velocity of cutting, and that comes out to be 2893.518 mm per minute, and in generally in mm per second it will be 48.2253 mm per second. Okay, this is for tungsten, and here we are set to calculate the cutting velocity. So we have calculated, this is the answer. And in next case for steel it is given, we are having an accelerating voltage of 150 kilovolts. Okay, for that 150 kilovolts we need to calculate the range. So before calculating range, we will see how fast the electron is traveling, that is VE. Okay, and we said it for an empirical formula, VE is equal to 600 into root V. So we'll substitute here 600 into the root V is nothing but root over 150 into 10 power 3 volts, and here this comes out to be 2.32 into 10 power 5 kilometer per second, nothing but 2.32 lakh kilometer per second. This is the speed of the electron with which it travels. I mean, it is having such a high kinetic energy once it was projected onto the workpiece. And generally this if you can observe, it is 2.32 is less than 3 lakh kilometer per second, and that 3 lakh kilometer is nothing but the speed of the light, generally denoted by c. Okay, so electron is traveling even in less than the velocity of light, but it is higher, 2.32 kilometer per second. It is traveling at that higher velocity. When it strikes the workpiece, it can travel due to only some distance into the workpiece, and that there will be resistance due to the lattice, whatever we discussed, and that we need to find how much penetration it will have, that is but the range. And for that we were given an empirical relation 2.6 into 10 power minus 17 V square upon rho. You need to remember these two empirical relations for electric discharge machining. Okay, and this is equal to 2.6 into 10 power minus 17. The V was given in the question 115 to 10 power 3 square, nothing but 150 kilowatts, upon the density rho was given in the question, and the density rho was given as 76 into 10 power minus 7. You can observe here, and the density rho was given 76 into 10 power minus 7 is not written here, 10 power minus 7. 10 power minus 7, and from this we will be getting the value of delta, and that comes out to be 76.973 microns. Mean 76.973 micrometers only it can penetrate into the workpiece. Okay, even so the depth of penetration will be less, but the velocity of cutting will be very fast, since we are this electrons is having a high kinetic energy. Okay, and here comes our next question. This is a good question. These questions, once you know the concept, then any question can be solved in an easy manner. So what I will do is, without reading this question, first I will explain the concept, then we will come back to this question, and then it will be very easy to solve. So for that we need to understand the concept first. This is the functioning of an CNC, computer numerical control devices. Okay, generally in CNC we will be having two types. One is the open type, and the other is called the closed type. Open loop type and closed loop type. What is the open loop type and closed loop type? The open loop type is, here we don't have any feedback mechanism. Okay, so what exact functioning is happening during the cutting is not known to the machine, is not known to the computer. Just its work is to give the pulse train. So with the help of a pulse generator we will be giving the pulse, that all we will discuss. Generally the pulse train is nothing but the periodic form of a pulse, and that periodic form generally will be a square stepped function. Pulse train will be given. Okay, that also we will see in the block diagram next. It is given to the stepping motor, or it is called as a stepper motor. Okay, and the stepper motor will have steps. So if you are giving one pulse, it will rotate by one step. In that way, suppose the stepper motor is designed for 200 steps for one revolution, then we need to give 200 pulses to get it turned by one revolution. For getting here one revolution, the stepper motor had turned 200 steps, say suppose. Then we need to give 200 pulses to the pulse generator. Okay, we need to give the 200 pulses for the pulse generator, and from that we'll be getting one revolution here, and that generally that one revolution will be, see, we are not giving only once and leaving, we are continuously giving, right? So this one revolution is nothing but it will be having from a revolution per second or revolution per minute. How many revolutions per minute? We'll be having some speed, so that speed is generally used with gearbox. So for our requirement, if we be in high speed, then we will be using an increasing the speed gearbox, or if we are into reduction, then we'll be using reduction gearbox. Okay, depending, we'll be using a gearbox, and that power will be given to the lead screw, so it drives a lead screw. So here we'll be creating a rotation, and the same is given to the lead screw. And once the lead screw starts rotating, we know the lead screw function is to convert the rotary motion into linear motion. So this gives our table the linear motion, nothing but the feed. Okay, in this way, on the table we'll be placing our workpiece whatever needed, and that will be machined using the whatever we will be using the numerical control milling machine or even drilling machine. So generally we'll be using this for point-to-point application, and here we'll be using a incremental mode of giving input, because in stepper motor it is happening in a step-by-step manner, right? So we'll be using incremental mode of input. So this is all about open loop. We'll discuss it in detail. This is the most important thing for us. The other is the closed loop control system, and always remember, in open loop we'll be using the stepper motors, and in closed loop we'll be using the servo motors. And servo motors are generally two types. One is the AC servo motor, and other will be the DC servo motors. And these closed loops are used with a feedback signal. So whatever is happening on this table, whether it is moving forward, whether it is coming back, is there any problem in moving, or is there any requirement to change the position, that all there will be a sensor. Okay, this sensor will be generally encoder. It will convert this mechanical output into a digital code, and it will send into the comparator again. That comparator again, it will be sent into an AC generator, and from that we will be giving power to the DC servo motor, and from DC servo motor again to the gear, and again to the gear to the lead box. Here we will be having a feedback loop, so that helps us in knowing where our position is, and at what position we are. Is there any change in position needed? But in servo motor, it blindly gives the power and it starts running the motor. In stepper motor, that is an open loop. So here our question is about open loop. We'll discuss the one basic example here. After discussing the basic example, we'll go into that question. Then it will be a very easy question. This is the block diagram for our open loop CNC, computer numerical control machine, and here we'll be giving our power supply. Mostly it will be the DC power supply, and that power supply is given to the pulse generator. So this device generate pulses in the form of a pulse train. Pulse train is nothing but it will be continuously providing a step function. See here, the upper part means it is given some voltage, and here the lower part means it is not given any voltage. Again, upper part means given some voltage. It will be like a step function. We know the step function in the mathematics, right? So this is a step function, nothing but a square function, square train here, square pulse train. Okay, this is called as the pulse train. So the motor operates. This is called a stepper motor. And stepper motor working, you can refer some video anywhere in some YouTube, then you will understand how exactly stepper motor works. In stepper motor, there will be several steps, and there will be magnets everywhere. Whenever once one part of the armature is magnetized, it will make one step. So whenever we are giving one pulse, it will be forming one step there. Again, for other pulse, it will be taking one more step. Again, for other pulse, it will be taking one more step. And that as a step, we are giving continuous power supply. The pulse train is also continuous. Then the stepper motor also continuously rotates with some angles, right? And then it will be making one revolution overall. It will be making some revolutions here. And here we will be using a gearbox to control the speed, whether we need to increase or decrease, we just discussed. So here we will be using gearbox, and this gearbox will be giving power to the lead screw. Then this is the lead screw. It is having a screw threads here. This is the lead screw, and this is called the table on which we place our workpiece. This is the lead screw. Okay, and lead screw, we know the screw will be having some pitch. Since it is a lead screw, generally it will be a single start thread where we are using. Then we'll have some lead screw will have some pitch, and the lead is nothing but the distance traversed by the table for one revolution of the lead screw, and that will be generally equal to the pitch of the lead screw. And we know what will be the pitch of the lead screw. It will be the distance between two consecutive crest or two consecutive trough. This will be the pitch. Okay, this is all about the functioning, and we'll see how it functions. Suppose I'm taking an example here. I'm taking an example. Suppose our gearbox is having a generally gear ratio. Whenever it's at gear ratio, it is V output upon V input, right? Okay, and suppose if our gear ratio is say 2, then what does it mean? If you are giving an input of suppose if gear ratio is 2, if you are giving an input of 1 meter per second, then our output will be increased by 2. If you are giving 1 meter per second, then output will be getting 2 meter per second. If you are, suppose the gear ratio is 1/2, we will take one more example of reduction. Suppose your gear ratio is 1/2. What does it mean? If you are giving input of 2 meter per second, then output will be 1 meter per second. So in this way, we will be changing the output speed by providing a gearbox. So what I am telling is, we know one step gives one pulse. Nothing but for one pulse from the pulse generator, our stepper motor will rotate by one step. Okay, so in this way we'll be having a stepper motor. Here there will be all the armatures here, armature coils. Okay, in middle we'll be having our shaft. Okay, in middle we'll be having some shaft, and on normal armature coil will be giving power to these armature coils. Each time one coil will be powered. Suppose if this coil is powered, our magnet whatever is there, will just come into position with this. Next this will be powered. Then again our stepper motor will turn in this way and it will come to here. Again it will be powered, it will come to here. In that way, for each step of power it will be turning, it will be rotating. So after finishing the number of steps, suppose the number of steps, let the number of steps be some 200. I'm just stopping this. Let the number of steps be 200. So for 200 steps, what does the 200 steps mean here? The 200 steps mean is, if our stepper motor turns 200 steps, then it makes one revolution of its shaft, its own shaft. So this shaft will turn one revolution. So when the stepper motor makes 200 steps, it will take one revolution. How will we make the stepper motor to turn 200 steps? So we need to give 200 pulses. So for 200 pulses input, our stepper motor will make 200 steps, and that will give us one revolution of our shaft of the stepper motor. So if this one revolution of the shaft of the stepper motor is connected to the say suppose our gearbox, okay, if it is connected to the gearbox, or for some time, remember there is think that there is no gearbox, then what will happen? This one revolution will be directly given to the lead screw, right? So the lead screw also will make the one revolution, and we know when the lead screw makes one revolution, the table will traverse by PMM, nothing but the pitch, whatever be the pitch, it will travel by PMM. Okay, whenever we give 200 pulses, the stepper motor makes 200 steps. That is equivalent to one revolution of the stepper motor, and if it is directly converted to the lead screw, then it will make PMM of revolution. And now consider we are having our gearbox, and it is having a output of gear ratio as 1/2. Then what will happen? We'll give the same 200 pulses, and we will be using the same 200 steps of the stepper motor. For that, it will produce one revolution of the stepper motor shaft, and when it is connected to the gear, what happens is, we know the input is 1, then what will be the output? Output will be 1/2. So then it is nothing but, it will revolve 1/2 revolution of the lead screw. And what is the 1/2 revolution of the lead screw leads to? Nothing but P/2 mm distance traversed by the table. See, for one revolution of the lead screw, it is traveling P/mm. For 1/2 revolution of the lead screw, it will travel P/2. And this generally, this P, when the gear ratio used, this P/2 is called as the effective, P effective, nothing but the effective pitch. Okay, that will be used here. And one more things here, some terms you need to understand is, for the first term is called as BLU. The BLU is called as the basic length unit. Here we will not discuss too much here. We will separately discuss in concept series this complete open loop circuit CNC, and also the closed loop CNC also. There are also questions possible on closed loop CNC. Both are generally same for our BTech level. This same closed loop CNC we will be using in mechatronics. There we will be using the encoders and decoders. Then we will be using it full-fledged. So here this is all basic. This basic, if you can understand there, it will be very easy. Mostly there can be a possibility of question asked in GATE also, because this is in syllabus. So the BLU, basic length unit. is generally called as the displacement. You need to note this important. The displacement of the table per one pulse generated from the pulse generator. One pulse generated from pulse generator. What does it mean? Distance traveled per one pulse. Here in the question, if you can see, when we are giving 200 pulses, then it is making PMM of revolution, PMM of table travel. So for 200 pulses, this is for, I am taking for example, how will you calculate BLU? So for 200 pulses in our above example, it is making PMM of the table travel. Then what it will make for one pulse? So for one pulse, what will be the displacement of this table? That is named as BLU. And from here the BLU can be calculated as BLU is equal to P upon 200. Okay, suppose in our question, suppose in our 1 mark question, say suppose there if pitch was given as 4 mm and it is said that we are using a stepper motor having 100 steps, then what we'll do, they are asked to calculate BLU. Then simply you can say BLU is equal to P 4 mm upon 100 and think about 0.04 mm. So 0.04 mm will be the basic length unit here. Okay, and this is all the basics required for this question. We'll just go into the question. It was already got late. So in a feed drive of a point-to-point CNC, as I said, it will be used for point-to-point applications also. CNC drive, a stepper motor rotating at 200 steps per revolution. Here it is given, it is used 200 steps. Drives a table through a gearbox. Here we are having gearbox and a lead screw nut mechanism, which is having a pitch of 4 mm. The pitch of the lead screw was also given. And the output to the input speed, nothing but the speed ratio, gear ratio, that is given as 1 upon 4. Right. And a stepper motor driven by the voltage pulses from a pulse generator S and executes one step per pulse. As we know, for one pulse we will be getting one step. Okay, the frequency of the pulse train from the pulse generator is 10,000 pulses per minute. So in 1 minute this pulse generator will be producing 10,000 pulses. That means in 1 minute our stepper motor will make 10,000 steps. If 10,000 steps make if 200 steps make one revolution, then what is the number of revolutions made in 1 minute? Nothing but 10,000 upon 200, right? And that comes out to be 50. So it will be making 50 revolutions per minute. Not exactly. So it will be making 50 revolutions per minute. That is the speed of the stepper motor. Okay. So this is all the question. And in the question, first thing was to ask to calculate the BLU. I just now said how to calculate BLU. Here in the question, for 200 pulses, nothing but 200 pulses, every time you write the same in the same order. For 200 pulses we are getting 200 steps, nothing but the stepper motor is making 200 steps per revolution. That gives one revolution of the stepper motor shaft. And here the speed ratio was given 1 by 4. What does that 1 by 4 mean? If you revolve our stepper shaft by one revolution, after the gear it will be making 1/4 of the revolution on the lead screw. If it is making 1/4 on the revolution of the lead screw, then it will be making P by 4 mm travel of the table, right? So this P by 4 is called as the effective pitch, nothing but 4 by 4, that is 1 mm. Okay, so directly we can write for 200 pulses. We'll relate these both. For 200 pulses we are getting 1 mm, nothing but P by 4, right? Then we need to calculate BLU. For BLU, what I said, the displacement made for one pulse. So for one pulse, what will be the displacement? That displacement is nothing but BLU. So from this we will be getting the BLU, and the BLU comes out to be 1 upon 200, and that comes out to be 5 microns. Okay, and this is your answer to the first question. And the next question is, a customer insists on a modification to change the BLU to 10 microns without changing the table speed. So the customer wants to make the modification and he don't want to change the table speed. So how will we calculate the table speed here? Simple. It is said in the question, for one pulse, nothing but the for BLU will say, for one pulse we are getting 5 microns on the table feet, right? Nothing but the BLU. So 5 microns is nothing but 5 into 10 power minus 3 mm on the table feed. And it is said in the question, frequency was given 10,000 pulses per minute. Then for 10,000 pulses per minute, what will it be? What linear distance it will make per minute? It is nothing but 50 mm per minute. It will make 50 mm per minute, and this is called as the table speed. Okay, this is called the table speed, and it is said that keeping this table speed constant, a customer needs some other specifications. So we'll solve the question further. A customer insists a modification of change to BLU to 10 microns. Now the customer wants a BLU of 10 microns without changing the table speed. Okay, then what should be the new speed ratio and the frequency required? So to make the changes what the customer needs, what should be our new speed ratio? Nothing but the value of U dash, let it be U dash, and also the frequency required here, F dash. Okay, we need to calculate the both. So now here our table speed was set to be constant, and V table that is 50 mm per minute, right? And now the new BLU the customer need is 10 microns, so nothing but 10 into 10 power minus 3 mm. Okay, and now we know one pulse, one BLU means nothing but one pulse. We need to produce BLU, we need to make a displacement of BLU, nothing but 10 into 10 power minus 3, right? So now for making this table speed here 50 mm per minute, for one pulse we need 10 into 10 power minus 3 mm of the displacement. Then for 50 mm of displacement in a minute, how many pulses should be generated in a minute? That will be our new F dash. With a cool mind, you understand, it will be very easy. So the F dash we'll be getting the F dash as 5000 pulses per minute after calculation. Okay, this is our new frequency value. Now we need to know the new gear ratio. Simple. For the old gear ratio, what we are having, U is equal nothing but gear ratio. There it is a speed ratio. For U is equal to 1/4, we are having BLU of 5 into 10 power minus 3 mm. It is directly proportional to BLU, right? Because the 200 steps of motor is constant. That it is so nothing will change, but the pulse frequency is changing, but the table speed will be remaining constant, right? For that we just need to relate the speed ratio and the BLU. Okay, for initial whatever we calculated BLU of 5 into 10 power minus 3 mm, it is given initially we are using a speed ratio of 1/4. Now the customer said he need a BLU of 10 microns, so 10 into 10 power minus 3 mm. What will be our new speed ratio? That let it be U dash, and that U dash comes out to be 1/2. Okay, this is our new speed ratio. This is our answer, and this is our new frequency required. This is our answer. So in this way you understand the concept, it will be very easy. And the next question, this is an interesting question. Generally this question is not dealt for us, but there is a probability of getting this. Okay, even in engineering services mains there is a probability. Even in general studies there will be a probability. This is on powder metallurgy. Maybe in gate examination there is a possibility of getting, because this was discussed in NPTEL videos, right? So there is a possibility of getting in gate also. So you understand, I'll be explaining it in a very easy manner. You just understand. Okay, we'll do one thing. This question will be making a separate video. Here we'll end this video because by now it is already too long time. We'll end this. We'll make a separate video for only this 5th question. It is a very interesting question, right? Thanks for watching till here. Thank you. Let's continue with the 5th question there.